Hi, I am Shagni Chatterjee, and together with my advisor, Dr. Debajyoti Bera, we present our paper titled Applying the Quantum Alternating Operator Ansatz to the Graph Matching Problem. First, we define matching in graphs. A matching is a set of independent edges of G. By independent edges, we mean edges which are vertex disjoint. For example, in the graph before you, each of the individual edges themselves can be considered a matching. We also have the trivial matching, which is the empty matching. Some examples of matchings of size 2 are M1, which has E1 and E3, also M2, E2 and E4. Note that there are many other matchings like E1 and E4, E2 and E5, and so on and so forth. However, the matching of maximum size in this graph is 2. Like the matching size is 2. This is a combinatorial optimization problem. This is solved using a linear program which is given as follows. We define a variable for every edge of the graph and a constraint for every vertex of the graph. We maximize the total number of edges subject to the constraint that the total number of edges incident on a particular vertex is at most 1. The motivation for applying our QAOA algorithm to the graph matching problem is as follows. Counting problems with respect to matchings are sharply hard. This was proved by Valiant in 1979. This result also extends to bipartite matchings. Since counting problems are sharply hard, we do not know of any efficient deterministic algorithms that can create a superposition over all matchings with non-zero amplitudes. Similarly, we do not know of any efficient deterministic algorithms which can create superposition over other subsets of matchings with non-zero amplitudes like maximal matchings. Using matching as a underlying problem, we wanted to develop a framework so that we can use and analyze this algorithm for other harder problems like independent sets of vertex covers for which even the search problems are NP complete. Finally, we wanted to theoretically analyze the effect of quantum inputs, that is, what happens when you give a superposition over matchings instead of just classical inputs, which are individual matchings, to the QAOA plus algorithm. Now we define what we mean by the QAOA plus algorithm briefly. The quantum approximate optimization algorithm was defined by Fari, Goldstone, and Goodman in 2014. It was developed on the back of the quantum adiabatic theorem. This is a parameterized algorithm that produces approximate solutions for unconstrained combinatorial optimization problems. In 2019, Hadfield et al. Gave the quantum alternating operator ansatz, which is an extension to the original QAOA, in which they showed that by replacing the fixed unitaries given in the original paper by general parameterized unitaries, we can produce approximate solutions for constrained optimization problems. What do you mean by constrained and unconstrained optimization problems? So if you have a combinatorial problem of n variables, the configuration space is a proper subset of the entire, the feasible subspace is a proper subset of the entire configuration space. This is the case for a matching problem in which we can see clearly that not all edges, not all subsets of edges form a matching. We show the QAOA diagram. This is a diagrammatic version of a QAOA circuit. We see that first we have the initial state and then we apply two sets of unitaries in alternation p times. The first unitary represented by the red boxes are the phase separation unitaries. while the second set of unitaries represented by the blue boxes are the mixing unitaries. We define the we lay out the algorithm as follows. Our input parameters are of three kinds. We have the natural number p, and we have p sets of parameters gamma and beta, which act on the unit parameters unitaries up and respectively. Our output is a string z that approximately optimizes our objective function. In this case, we want to have a string z which maximizes the matching of our graph. Every individual bit in our string represents an edge of the graph. We initialize the starting state S. An important point about the starting state is that it should be efficiently preparable from the all zero state. If not, then we lose any speed up we get from the quantum algorithm. While true, we use this circuit on a quantum computer to calculate the state gamma beta as shown in the figure. We calculate the expectation of the gamma beta state as Fp. We measure the gamma beta state in the computational basis to get a string z, and we repeat. We evaluate the objective value of the string, and we repeat this process of applying the unitaries to the state S by optimizing the parameters till we get an objective value which is at least equal to the greater than or at least equal to the expected value of our gamma beta state. For example, first we show that we use the linear program for our maximum matching in order to develop our two sets of unitaries. The phase separation unitary is defined as follows. We create the cost Hamiltonian from the objective function using Boolean composition rules. And we create the mixing unitary by encoding the constraints into appropriate Hamiltonians. We see that the consolidated unitary is nothing but applying the individual mixing unitaries to each individual edge of the graph. The entire point of the mixing unitary is to evolve the state from one feasible state to another, and the phase separation unitary encodes the objective function. So that at the end of one layer of applying both of these, we have certain states that have certain values of the encoding function, of the objective function. This is a circuit for the graph that we saw earlier. The first layer of all Z rotation gates corresponds to our phase separation unitary, and the entire circuit after it until the measurements start is the consolidated mixing unitary. We can note that there are individual unitaries, mixing unitaries applied to each of the edges given in the diagram. We came up with the decision tree technique to analyze what happens in the circuit for both classical and quantum cases. The diagram represented in front of you, the figure shows what happens when you apply the QAOA plus or QAOA plus circuit on a triangle graph. We see that we get an output which consists of all matchings with non-zero amplitudes, all feasible matchings. When we apply this to a quantum input such as the W1 state, which in this context can be thought of as a uniform superposition over all single edges, we have a superposition, the output state is a superposition over all edges of over all possible matchings other than the empty matching. Everything has non-zero amplitude in this. The main results of this paper are as follows. We can theoretically prove that applying our QAOA plus algorithm to the initial state 0n, which signifies the empty matching, we get a superposition over all distinct matchings with non-zero amplitudes in p equal to 1. And An experimental output of our theorem is shown here. We ran the algorithm, the circuit on the QSM simulator of Qiskit and got the following output for the graph that we saw earlier. We see that all of the states are the feasible matchings and every matching is present in the output. We can also theoretically prove using the decision tree techniques that applying our algorithm to the initial state W1, we obtain an output state which is a superposition over all maximal matchings with non-zero amplitudes. This happens in expected number of phases less than or equal to twice the number of edges in the graph. Thirdly, we show that the QAOA plus output gives us a better expected matching size compared to the uniform distribution over all edges. We prove we prove this by showing that we prove this by determining the strict lower bound for the QAOA plus expected matching size, which we see in this figure. The red line shows us the strict lower bound and the black line shows us the strict upper bound for our QAOA plus output, while the blue line shows us the expected matching size for a uniform distribution over all edges. An asymptotic view of this would be this, where we see that the strict lower bound is asymptotically equal to the expected matching size in the uniform distribution over all edges. We show the advantage of quantum inputs over classical inputs. We prove this for two regular graphs, which says that we get a better expected matching size in the quantum input case. This can be seen in the figure as shown here. The lilac bars give us the expected matching size for uniform distribution over all edges, while the blue bars show us the expected matching size using the quantum input, which is the W1 state, and the red bar shows us the expected matching size for the classical input or the empty matching case. This is shown for two regular graphs up to 10 vertices, and we can theoretically prove that this holds for all two regular graphs. A future work of this would be theoretically improving some of the lower bounds, such as we saw earlier. We would like to theoretically improve the strict lower bound so that it is strictly greater than the classical case. We would like to extend our results to general graphs instead of just two regular graphs. We would also like to use the decision tree technique that we developed in this paper on NP search problems like independent set or vertex cover. Thank you.